Welcome back, guys. Today we're looking at section 1.6 in our note packet, which is all about inverse functions. So we have 4 objectives for our lesson today. The first objective is we're going to find inverse functions informally and verify that two functions are inverses of each other. So if I give you two functions, can you tell me if they're inverses? Then we're going to use graphs of functions to decide whether functions have inverse functions. So we'll learn a nice little shortcut on does a graph doesn't even have an inverse. We're going to determine if functions are one-to-one. Okay, and we'll talk about what that means. And then we're going to focus on how to find inverse functions algebraically. So how do we find an inverse function? Just by doing the work. So really quickly, I guess I need to erase this because it's not all fitting onto one page, of course. Okay, so just a quick reminder of what an inverse function is from Algebra 2. So an inverse function means if I have coordinate points, like so, right, 1, 5, 2, 6, 3, 7, 4, 8, and so on and so forth. If I switch the x and y coordinates, so now it's 5, 1, 6, 2, 7, 3, 8, 4, then those two functions are inverses of each other. So they're functions where the x and y coordinates are flipped, and we'll talk about what it looks like on a graph as well. But then the only other thing, I guess, then to remind us of is the notation, right? So we would say f inverse of x. So this is not an exponent. It's the notation for an inverse function. So just making sure we know that. Now, definition of the inverse function is if I have two functions, f and g, and I plug g into f, and I get out x, right? My final answer is x. And then I plug f into g, and I get out x. Sorry, that's my dog. If I get out x on both times, then they are inverse functions of each other. So I'm going to show you what that means here on our first example. Oops, I got a little jumpy here. Okay, so let's look at example 1 and 2. So example 1 and 2 say find the inverse function of f of x equals 4x. Okay, but then verify that they actually are inverses of each other. So to find the inverse function, hopefully this is something we remember from Algebra 2. Remember that f of x is just another way to write y, right? So to find the inverse function, you just switch the x and y. So this will now be x equals 4y. And then you solve for y. So I'm going to divide by 4, and I get x over 4 equals y. So then this tells me that f inverse of x is equal to x over 4. And that is the inverse function of f of x, right? Then the second part is to verify that they are equal to each other. So what that means is that I'm going to take my inverse function, f inverse, and I'm going to plug it in to the original function. So this is going in right there. So I have 4 times, and then my inverse function is x over 4. So the 4's cancel, and I just get x. So that's good, because that's what we want, right? That's what we're looking for. But it has to go both ways. So now we're going to take the original function and plug it into the inverse. So that means now that this 4x is getting plugged in right there, which gives me 4x on top and a 4 on bottom. Again, the 4's cancel, and I just get x. So because I get x whether, like no matter what direction I plug in these two functions into each other, because I x both times, then I know that it is a function. Okay, so go ahead and try this one. You're going to repeat the same thing. You're going to find the inverse function by switching the x and y and solving for y. And then you're going to verify that they actually are inverses of each other. And then when you're ready to go ahead and hit play and we'll go over it. Okay, so let's go over this one now. So if I change that f of x to y, I have y equals x minus 6, and then I'm going to switch the x and y, and then solve for y. So I get x plus, excuse me, 6 equals y. So that tells me that the inverse function of f is x plus 6. So there's the first part. I found the inverse function. Now I want to verify. So, and the order in which you do this doesn't matter, but I'm going to plug the inverse function into the original function first. So again, this is going in right there. Okay, so instead of x minus 6, it's x plus 6 minus 6. You don't really need the parentheses, but sometimes it's helpful to see that I'm taking my x plus 6 and I'm plugging it in for x. Well, the 6's cancel, and I just get x. So that's good. Now let's go the other way and plug the original function into the inverse function. So now I'm taking this and I'm plugging it in for x right there. So now I have x minus 6 plus 6, which again, the 6's cancel and I just get x. So these are, in fact, inverse functions of each other. So that's what you're looking for. If you plug them into each other and you get the inverse, then you're good to go. And they are inverse functions of each other. So let's look at a couple more examples, ones that get a little bit more tricky, maybe. So I'm going to do, well, we'll do them all together. How's that? That'll be fine. So I want to verify that both of these are inverse functions of each other. So what that means is that I have to plug f into g and I have to plug g into f. Again, it doesn't matter the order that you do this. So I'm going to start by plugging g into f. So again, this is going in right there. So I have 2 times, and then instead of x, I have the cube root of x plus 1 over 2 cubed minus 1. So all I did was replace x with g of x. Well, cube root and a cube cancel, so that's nice. So that gives me 2 times x plus 1 over 2 minus 1. Well, the 2's can cancel, right? 2 divided by 2 is 1. So I get x plus 1 minus 1, which equals x. Woohoo! So it works one direction. But now I actually have to verify both, because if it works in one direction but it doesn't work in the other, then they're not inverses of each other. So here I have now g of f of x, which just means that I'm going the opposite way, right? I'm taking my 2 x cubed minus 1 and plugging it in for x. So I have the cube root of 2x cubed minus 1 plus 1 all over 2. Well, the 1's cancel. So I have the cube root of 2x cubed over 2. Well, the 2's can cancel. So I get the cube root of x cubed, which just equals x. So I have verified that these are actually inverses of each other, because when I plug them into each other in both directions, I get the value of x. Now it has to be x. It can't be negative x. It can't be x plus 1. It can't be anything like that. It just has to be 1x. So here, let's do b. Let's just do it together. And we're going to do the same thing. I'm going to take f of g of x. So that means I'm taking g and I'm plugging it in. So I have the square root of x minus 1 squared plus 1. Again, the square root and the square can cancel, so I get x minus 1 plus 1. So this one's a lot easier. Boom, x, done. Now I want to go the other way where I plug f into g. So I'm going to have the square root of x squared plus 1, and then still that minus 1. Well, again, the 1's cancel, so I get the square root of x squared, which is just x. So these are, in fact, inverses of each other. Hopefully we're feeling pretty good about this. We did cover this in Algebra 2, but it should be a nice little refresher here. And then the last part of this objective is asking us which of these two functions is the inverse function of this. Is it g of x or is it h of x? So what we're going to do is I'm going to take my f of x, this guy right here, and I'm going to plug it in. Actually, you know what's easier? Let's just solve for it and see which one it is, right? So f inverse, let's just find what the inverse of f is. So let's do y equals 5 over x minus 2. Let's switch the x and y, and we're going to solve. So in this case, I need to get rid of my denominator, so I'm going to multiply by y minus 2. And I'm just going to leave that there. X times y minus 2 equals 5. Okay, now I'm going to divide by x. So these guys cancel. I'm running out of room, and I get y minus 2 equals 5 over x. And then add 2 to the other side. So I have 5 over x plus 2. So which one of those? So f inverse is 5 over x plus 2. So which one of these is the inverse? And it's my h of x. That's probably faster than plugging in f of x into both of these. Okay, so the next part, the next objective that we're looking at is showing that two functions are inverses graphically, so you will need a graphing calculator. So just make sure you have that out. If you need to hit pause and go get it, that's fine. But we're going to move on here to example 5. And we're going to show that these two are inverse functions of each other, both graphically and numerically. But before we get started on that, we need to talk about this right here. So two functions are inverses of each other graphically if they are symmetrical around this line, y equals x. So just a quick reminder that the line y equals x is that perfect diagonal through the origin. Okay, so if they are symmetrical to each other over about this line, y equals x, then they are inverses of each other. And we will see what that looks like both down here, but also on this problem as well, okay? So let's start with verifying this numerically, just because we can. Actually, we probably feel pretty good about figuring this out numerically. Let's just show you graphically, and if you want to test it out numerically, you can. So I'm just going to show you then how to do this on your graphing calculator because it's probably faster. So what I'm going to do is the first thing I need is f of g. I need to know what that graph is, right? So I'm going to graph this. So I'm going to take g, I'm going to plug it in for f, right? And I have 2 times, oh, we already did this one, that's why we don't have to show it. The cube root of x plus 1 over 2 minus 1. Okay, and then the other direction, when I plug f into g, I get the cube root of 2x cubed minus 1 plus 1 over 2. And so these are the two functions that I'm going to enter into my calculator because, so I'm going to call one y1 and the other one y2. Because if they are inverses of each other, they will both get us the equation y equals x. They will line up at the equation y equals x. So I'm going to pull up my graphing calculator and we're going to enter this and just show how they are both equal to the line y equals x. Alrighty, so here's my graphing calculator. And in y1, I'm going to go ahead and enter that first equation, being very, very careful with parentheses. Okay, so I have 2 times, now I'm going to do the cube root. Now, cube root is under math. I'm actually going to do another parenthesis here, but then we're going to go math, and then cube root is right here, number 4. So the cube root of x plus 1. Now the cube root, and I'm actually going to do another parenthesis here, because it's the cube root of x plus 1 on top, and then divided by 2, right? So the whole thing is being cube rooted. So close, close, and then I'm going to raise it to the third power, just making sure I don't have a typo here, minus 1. So there's the first one. And then the second one, I'm going to go back into math, and I need the cube root of 2x cubed minus 1 plus 1, I'm going to close it again, divided by 2. And then I'm also going to graph the line y equals x, just to show you, and I'm going to make this a dashed line. It's kind of hard to do on my calculator here. There, that's probably better. Okay, oops. Alrighty, just to show it's a dashed line, okay? So then I'm going to hit graph. I'm actually going to do zoom 6 because I don't know what my window looks like. So there is the first graph, which is lining up with y equals x. There's the second graph, which is also lining up with y equals x. And then, of course, you can barely tell, but the third graph in black is y equals x. So since all three of them are the same line, they are inverses of each other. You can also use the table feature to show that y1 and y2 are the same. Since they're the same, they are inverses of each other. Okay, so that's how we do it kind of algebra or using our graphing calculator. Let's show now how to graph the inverses by hand. And I'm going to do my very best here to make it pretty, okay? So when we're looking here, I'm going to be switching colors, right? We know that they are going to be reflected over this line y equals x, which is this. Perfect. Dashed line. Holy moly, am I off? But you get the idea, okay? There's that line. But sometimes it's kind of hard, like looking at this graph, I'm like, how do I reflect it over this line, right? It's like kind of tricky. The good news is that it's really not that tricky. All we're gonna do is we're gonna switch the x and y coordinates, right? Because that's the other definition of inverse. It's just the x and y coordinates just flip. So like, for example, this point right here is the point 3, 0. So then if I switch that, I get 0, 3. So my new point is going to be 0, 3. Okay, then I find this point too. I have 4, 1. So if I switch that, I get 1, 4. Same thing, like I can keep going. Sometimes I like to find like this one's kind of at 5, 8-ish. So then at 8, 5 is another point. And I can keep going, right? 2, negative 1. So if I switch that, it'll be negative 1, 2. Sorry, my dog is cuddling with me and she's scratching herself. Okay, there we go. My computer is moving all over the place. And then another point I see is like negative 1, negative 7 looks like a good one. So negative 7, 1. And then when I go to connect those beautifully, right? I get my inverse graph. Okay, so you don't really need to draw this line, y equals x. You should just be able to find the inverse just by switching the x and y coordinates. Okay, so let's look over here. 1, 1. If I switch that, it's still 1, 1, right? Let's see if I can find some other points, like maybe like 3, 1/2-ish. So like 1/2, 3. Okay. What about like maybe like 2/3, 2? So then 2, 2/3. So what actually happens on this graph is the inverse lies right on top of itself. Because if we think of that line, y equals x again, it's probably better the faster I go. There we go. Do you see how this graph is perfectly symmetrical over this line, right? Like if I were to fold this piece of paper in half along this red line, the graph would actually line up on itself on either side. So this is actually already, or the inverse is just on top of itself. So you don't actually have to draw anything else here. Okay, so hopefully we're feeling good about drawing the inverse. Just switch the x and y coordinates. We're now going to look at how do you even know if there is an inverse function, right? So there might be graphs that don't have an inverse. You cannot flip the x and y and have it work out. So that is what we call one-to-one. So that's what we're going to look at now. Is a function is one-to-one if it has an inverse, if the inverse function is one-to-one. So I guess I should say function is one-to-one if the inverse function is one-to-one, right? So, scroll down, come on. So we have the vertical line test to determine if something is a function, right? I can draw any vertical line and it'll tell me whether or not this is a function, right? So like this is a function, this one's all three of these are functions because they pass the vertical line test. Well, a function is one-to-one or a function has an inverse if it passes the horizontal line test. The horizontal line test is exactly the same as a vertical line test, just horizontal lines. So if I draw, that's not what I want. If I draw any horizontal line on a function, and it only touches that function at one spot, right? It only touches here, 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 here. Then that function has an inverse. So that function is one-to-one. 1, 2, 1. Because we say it has an inverse. So like here, if I draw any horizontal line, you see how it touches the graph in 2 spots? This means that this is not one-to-one. Not one-to-one. So this does not, 1, 2, 1. This does not have an inverse. This graph does not have an inverse. Same thing here, right here I touched the graph 4 times. 1, 2, 3, 4. So this is also not one-to-one. All good? So if determining whether or not something is a function, you use the vertical line test. But to determine if something has an inverse, then it used the horizontal line test. So last question here. Is the function f of x equals absolute value, square root of x plus 1, 1 to 1? So we can use now this feature up here, saying that if you plug in a on one side and you plug in b on the other side and you solve it and you get a equals b, then it does have an inverse. It is 1 to 1. So we're going to do that first, and then we're going to show you graphically as well. So if I plug in a plus 1 and I plug in b, so if I plug in a on one side, b on the other, and I'm going to solve. So I subtract 1, right? Those cancel, and I get the square root of a equals the square root of b. And if I want to get rid of the square roots, I can just square. And I get a equals b. Since I get a equals b, this is 1 to 1. It does have an inverse. Okay. If I got like a equals b plus 4, it would not be 1 to 1. Okay. The other thing is you can just think about what this graph looks like. This graph starts at 1 and it just goes like this. So is that going to pass the horizontal line test? Yes, it is, right? No matter what horizontal line I draw, it will only touch the graph one time. So it will be 1 to 1. So you can do it algebraically, or you can think of it graphically if you know what the graph looks like. All right, we are cruising. This is our last page, and it's just finding the inverse algebraically, which we have already done. So this should just be a pretty quick page here. Scroll down a little bit more. It's asking you to find the inverse function of f of x. So we already know our steps, but we'll write them down just in case. Replace f of x with y, right? That's first step. Second step, switch the x and y. And then third step is to solve for y. So nice and easy. This shouldn't take us very long. We should be good to go here. So let's go through the steps. So y equals 5 minus 3x over 2. So I replaced the the f of x with y. I'm going to switch the x and y. So x equals 5 minus 3y over 2. And I'm going to solve for y. So I'm going to multiply by 2, right? And I get 2x equals 5 minus 3y. Subtract my 5, so I have 2x minus 5 equals negative 3y. And then divide by 3. So I have 2x minus 5 over negative 3 equals y. And then once I have that, I can then go ahead and write f inverse of x is equal to 2x minus 5 over negative 3. And that is it. Yeah, not so bad. Just another quick review problem there. Okay, examples 8 and 9. These are our last couple problems here. Find the inverse functions of f of x equals x cubed minus 4 and f of x equals the square root of 2x minus 3. And then in the same viewing window, we're going to graph the function and its inverse, and we're going to see what it looks like. Okay, so let's just start with the first one. Okay, so f of x, let's just go into the y, right? We know what's going on, right? So y is equal to x cubed minus 4. So let's switch the x and y, and we're going to solve. So I'm going to add 4, x plus 4 equals y cubed. And then lastly, we have to take the cube root of both sides. Okay, so f inverse of x is equal to the cube root of x plus 4. So now what we're going to do is we're going to go into our graphing calculator and we're going to graph both of these in the same viewing window. So what that just means is I'm going to clear out these guys. And in y1, I'm just going to graph the original function, which is x cubed minus 4. And then in y2, I'm going to graph the inverse function, which is the cube root. So again, that's under math, right? Number 4. So the cube root of x plus 4. And I'm going to hit graph and see what it looks like. So there's one, and there's the other. So this is very similar to the one that we looked at on the previous page, right? And even then, let's go ahead and graph the y equals x again. Are these two graphs symmetrical over the line y equals x? And the answer is yes. If I had a mirror, if you hold up a mirror along this line, this red line will show up in the place of the blue line. So let's go ahead and do the second one now. Pretty confident it's going to be similar to the same, but you never know. So y is equal to the square root of 2x minus 3. We're going to switch the x and y. So I have now the square root of 2y minus 3. We're going to solve. So in order to get rid of this square root, I'm going to have to square both sides. So that gets me x squared equals 2y minus 3. Add 3 to the other side. Divide by 2. And that gives me my y function, or my inverse function, excuse me. I have f of x equals f inverse of x, x squared plus 3 over 2. So again, I'm going to go back to my calculator, and we're going to look at this. So I'm going to graph the original function up top, which is the square root. Actually, I'm just going to clear it because I don't want to make a mess. Okay, the square root of 2x minus 3. And then the inverse of this is, I'm going to put the top in parentheses, x squared plus 3 divided by 2. Let's see what this looks like. Okay, so something weird just happened because this is my original function, which is square root, so that looks right. So I don't know where this other line is coming from, right? Because really what's reflected over the x-axis is just from 0 to infinity, this part of the red line. So something weird happened to show this guy as well. And so what happens is we have to restrict the domain here because I can only look at what is actually symmetrical to my original function, So I have to start at 0 and then go to infinity. All of this stuff to the left, I'm not allowed to have because I don't have that continuing on down here. Okay, so this tells me that I just have to restrict my domain and x has to be greater than or equal to 0. Okay, or you can write 0 to infinity, which is fine too. So something to note here is the range. So my output of f of x, okay, is the domain of my inverse function. And I'll say that again, and we'll go back to the graphing calculator again to show that. The range of this function is 0 to infinity, right? The blue one is my original, that's my f of x. My range is from 0 all the way up to infinity. That is then the domain of my inverse function, 0 to infinity. Okay, so if my range of this function is restricted, then my domain of the inverse is also restricted. So we do kind of have to pay attention here, saying, okay, the only numbers I'm allowed to get out of this function are numbers that are 0 and bigger, right? I'm never going to take the square root of something and get out a negative. So 0 and higher are my only options, which means that it is my only option for my domain on the inverse function. Okay, so the last thing we're going to do is we are going to try these 3 extra examples. So I want you to pause the video and do these 3, and then when you come back, I'll have the answers up and you can just check your work. So go ahead and hit pause, do the work, and then when you're ready, hit play again. All right, guys, so here's the answers for A, B, and C. Make sure you check your work, look it over. If you have any questions on these inverse functions, please make sure that you reach out. Let me know. Send me an email, message me on Remind, whatever you need to do, because it's going to be actually kind of important. Well, all of it's important, right? But it's actually going to be important as we go on into Unit 3. Actually, we're going to be using more of our inverse functions. So you want to make sure that you're feeling really confident with these now. Let me know if you have any help or if you have any questions. And otherwise, I'll see you later. Bye.